National Institute of Science, Education and Research in India. But most of the work that he's presenting today was done at Monash University in Australia. So Priyaddarshi also spent a part of his previous research time in Germany.
Germany and Switzerland.
Where he spent many years at Monash University as a PhD research and later on as a postdoctoral researcher. So today he's going to give us a tour for the composition of the lithosphere, especially the shallow part, and providing insights of the transition of the pre-tectonic to the modern tectonics. So with that, I'll give the rest time to Priyaddarshi, and then please leave about 10-15 minutes for interaction with our participants. Okay, so please.
Thanks for the excellent introduction, and thanks for inviting me. Yeah, and I can give you one relaxation right now. You can call me PD, just the abbreviation of Priyaddarshi. So if anyone, that's more easier, and more people know me by that name. So yeah, as I said, so today I'll just give a summary of what I have been doing for the last 6 years around from my PhD till the postdoc, mostly in Germany, Switzerland, and Australia. So it's mostly the work that I did, it dealt with how, in what form, the orogenic processes may have appeared on Earth, the time that I will speak about. So this picture I always like to start with, it tells us about the two most unique things among many others of the Earth that we have right now is the continents, and then the imprints on plate tectonics. So here you can see the beautiful mid-Atlantic ridge, and then of course the continents. So if I dig a bit more deeper into the plate tectonics, this is a very classical, I take the image from Britannica, but we are all used to this, or some variant of this picture, where it basically shows, the convergent, divergent, transform boundary, the subduction zone, the Andean type and the Pacific type. And then what we mostly are used to these things is that we try to see what rock types form at these different settings. And then we go back in time when we work on the Precambrian terrains, we try to find out those rock types and then try to link whether the same tectonic events may have happened at that time or not. But a very critical aspect of plate tectonics is shown by this picture is the interlinked network of these plate margins. As you can see here, these are the zones of a high deformation, be it convergent, divergent, or transform. And then these are all linked in terms of their global relative motions. So if you change one plate, it has some effect. Whether we can measure it or not, it's a different issue, but it has some effect on the other plates as well. And that's also the very essence of plate tectonics. So with that in mind, I'm sure that we're all aware of the big fight that's going on for the last few decades in earth sciences about when and how did the tectonics start. And this is just a picture I took from one of the paper where it is marked that how many estimates have been given so far. There are many more. I think this paper came in 2013, so there are multiple more. But it gives the gist of what I'm going to highlight is that you can have plate tectonics at 4.2. You can have plate tectonics at 0.8. So that covers more than 70% of the Earth's history, which means we haven't done a good job on delineating this time scale. But as more and more research happened, particularly in the last 10 or 8 years, oh, sorry, I just forgot. I just put a couple of slides to just show the two extreme variants. The 4.2 thing came from the very well-known Jackal-Jerkins, in particular, the inclusions within them, which are thought to be granitic and are supposed to form at a very low temperature and pressure conditions, similar to where andesitic magma form today, the subduction zones. And through that analogy, people thought, okay, then subduction zones, and thereby the tectonics may have been operating since more than 4 billion years ago. The other spectrum is at 0.8 GA. And people like Hamilton or Bostrom have worked a lot on this, and they are arguing based on the certain distinguished quote unquote, rock types that they think are the very diagnostic of the modern plate tectonics, in particular like ophiolites, ultra pressure rocks, the blue schists, and the jadeite, and so on and so forth. And this is just a diagram showing the distribution of these different rock types across the age of Earth. And what they're showing that most of these rock types are concentrated at around 600 with the sporadic occurrences in the Proterozoic. So they argued that initially they argued this could be the initiation of plate tectonics. But recent studies are more and more clarifying that perhaps this is the onset of modern style of plate tectonics, the plate tectonics that we see today. Now, what I always feel is this sometimes that when we take particularly one proxy or something like this, we end up in this situation that what we are looking at and what does it telling us? Each proxy is telling us something. It's not about the absence or presence, or maybe about that, but in totality, it is something saying perhaps more, perhaps the style of the plate tectonics or how it evolved. So assuming based on the recent discoveries that have been made, so we are kind of inching on this time zone that is between 2.5 to around 3.2 billion years, where people have missed putting up more and more estimates around the time window. This I have just highlighted a few, like the establishment of felsic continental crust, where Bruno Duin and Ming Tang's work have shown that we may have had the appearance of felsic or silicic upper continental crust. And that may have happened through voluminous felsic magmatism, which again they correlated based on the uniformitarian argument that it must have happened in subduction zones. And through that, they said that we must have, or we are likely to have the tectonics at that time. Second is an eclogative inclusions in diamonds, which Steve Shirey and Richardson did a decade back, where they found a change from periodic to eclogative inclusions. Eclogite, is a major form of the subduction considered to be rock type, and they started to find a change from eclogative inclusions in diamonds. So they thought, okay, perhaps around that time we are having oceanic lithosphere recycled deep into the mantle in some form, most likely subduction, and that's the source of these eclogative inclusions. Similarly, Mike Brown has been doing a lot of work and his group on peer metamorphism and when it appeared across the Earth. And they are saying that around 2.8 or 2.7-ish, exactly when we are starting the first proper examples of peer metamorphism. And then recently, there has been a work by Brenner which showed the Pilbara block in particular has shown some horizontal motion. Although it is not sure whether the horizontal motion, how it is connected to the other plate margins or not. As you can imagine, it's nearly impossible to do that unless we have all the polar coordinates for all the preserved terrains at that time. But still then they showed that there is some sort of horizontal motion at that time. So based on all this and many others, of course, people have been thinking that we may have had plate tectonics at around that time. Now, I particularly, being a blend of petrologist and partly into numerical modeling, I'm always interested in the metamorphic data sets in particular. Not to say I'm not interested in the others, but this a bit more. So this is a diagram I took from one of these papers in 18. So you can see this is the x-axis is the age of the Earth, the 0 being the present day. And then on the y-axis, what we have is the thermobaric ratio. What it effectively tells us is the peak metamorphic temperature divided by the pressure at which that peak temperature was attained. That's basically a proxy of the geotherm along which the metamorphism was happening. If you plot all the data sets that Brown, Mike, and Tim did, they have found that we are seeing some sort of paired metamorphism starting to appear around this time window, where the red ones showing a very high temperature metamorphism at shallow pressures, and then the green one is showing some sort of intermediate conditions. The intermediate between this one and this blue one, which appeared only 0.7, 0.8 years ago. Now, these blue ones represent very high pressure, but low temperature. So they represent this the blue schist and the ultra pressure metamorphic terrains or the rocks, which also the example that I showed from Bob Stern is that similar rocks. So they said if this and this is the extreme end members of metamorphism, then we have this one and an intermediate version appearing at around 2.7 to 2.8. And they argued that this is the first signature of paired metamorphism. Now, paired metamorphism is considered to be a very diagnostic of plate tectonics, of an asymmetric plate subduction or some sort of downwelling, which causes the isotherms to bend, creating a high pressure, low temperature, and a low pressure, high temperature zones. And that's the cause of this paired metamorphic belts, the classic work of Miyashiro and subsequent works. So based on this, what we can say is that perhaps if this is the true argument of plate tectonics, we may have some sort of plate tectonics developed. That's why I put the question mark. Or rather, we can say some sort of subduction, a convergent plate margin behavior is going on. But if that is true, then what does this signature tells us? Then it might be true that, according to Bob's term, what they were saying, that perhaps we are having the modern day plate tectonic scenario emerging at around this time. Now, what I have done so far is mostly concentrated around this time window. So what I thought is that if plate tectonics appeared in this time period, then what was its style? If it is not similar to the modern day plate tectonics, the argument is, of course, based on the preserved rock record and the idea that you don't have too many occurrences of this high pressure, low temperature rock types, although we have few sporadic occurrences, but not as high as compared to what we see in this time window. So if that is true, then there must be some physical argument to support this. Why should we have a different style of plate tectonics? The argument comes from the thermal evolution of the Earth. So this is the x-axis, which again shows the age of the Earth, 0 being the present day, and the y-axis shows the mantle temperature conditions casted in the parameter called mantle potential temperature. So if you see this diagram, this rectangular box represents the range of the mantle temperature that we see today. The average is around 1350. And then these are the different estimates given by different studies. For example, this red shade has come from the Harrisburg studies, which is based on non-arc basalts. Then this line is given by Coronaga based on a Euro ratio. And then this is a very recent one compiled again by the non-arc basalt, the Ghanaian Fang. So although there has been a different discrepancies in the exact amount and to the exact magnitude, how much mantle was hotter as compared to the present day, one thing is coming up that mantle was hotter, and at least by 100 degrees or more than today. So what does it say about the character of the plate tectonics, or why we should take this into consideration? The reason is the rheology, or the weakness or the strength of the rocks that we see, is extremely dependent on temperature. And it's inversely proportional. That means if temperature increases, the viscosity decreases, or vice versa. So what do you mean is that at a very high temperature, rocks lose their rigidity and become more and more deformable. So if you have a lithosphere made up of rocks which are not that rigid, then it's very hard to propagate lateral stresses for a long distance of the order of plates. And if you cannot do that, then you also cannot make plate tectonics. So if you apply stresses, the lithospheres will deform internally without getting into any translation or motion, horizontal motion. So that's been the case. People thought, okay, then if we have the high mantle conditions, then we may have the viscosity lower. And to add this temperature, why this temperature should have been higher in these cases, they're mostly the radioactive and also the higher accretion heat content of that time. Now, we do have some rocks of that age, like Archean preserved, although it's not awfully lot, because as you go back in time, the rock exposures also decrease. So approximately less than 10% of the present exposed rocks is less than 3 GA. And this poses an inherent limitation to our understanding. So often now people are realizing the best thing would be to combine the natural rock record, whatever is available, with some sort of theoretical calculations, either in terms of analog modeling or numerical modeling, to understand this kind of complex problems. So I particularly intended to, or I did numerical modeling and then calibrated against the model results against the natural rock record, in particular metamorphic rock record. So that's I will now show you. So I'll just show you first the modeling part. This I did during my PhD with Taras and Schumett in Germany and Switzerland. So basically what this shows is the initial setup of my model. So I was more interested in understanding how the continent collision zones would have developed at the high mantle conditions. The reason being subduction has been studied well at that point of time, at least extensively, if not well, and they're all indicating that high mantle potential temperatures have effect on the subduction style. But the problem often with subduction is that the subduction recycles the entire lithosphere. So it's very hard to calibrate the models with a natural rock record, except for the geochemistry part. So I thought, okay, let's do it for the orogenic record, the continental collision or accretionary processes, because we have the rocks preserved. Whatever rocks preserved belong to those categories. So based on that, I studied this continental collision. So this shows, the upper diagram shows the overall box model. It's like at least 1400 deep and 4,000 kilometer wide. And then as you can see, if I zoom in this part, we have two continental crust, or then the lithospheric mantle part, the continental crust are further divided into upper and lower. All these have different mechanical and chemical properties. And then this is the oceanic crust. And I varied the parameters of these models, of course, to take into account the Archean conditions. For example, the oceanic crust was varied from 8 to 20 kilometers in thickness. The continental crust was varied between 30 to 45 kilometers in thickness. Then we assign, as I said, different material properties to all these things, rheological and compositional. And then in particular, I cranked up the heat of the convecting mantle by 175 degrees above the present day. Actually, we did a series of models where the mantle is increased in steps, like 50, 75, 100, 125, like that. So I've just shown one model out of it. So this is the start of the model. When we start, the subductions went through some external push. But once the subductions become stabilized, we remove the push, and then the entire model evolves on its own. That means under the slab pull and the wedge push and the convecting mantle traction at the bottom, all these forces come into play. So if you see what happens after a certain time, because the mantle is very hot and therefore very weak, it cannot support the weight of the subducting lithosphere. And therefore the lithosphere, the oceanic lithosphere rather, subducts, but it also shows retreating phase of the subduction. So you get a massive slab rollback, if you may say so. And then once the subcontinental crust comes into the scenario of the convergence, then we see a slab break off because of the changes in the physical properties, which causes extensional stresses to develop in them. But once that happens, then the two continental plates kind of converge under the mantle traction provided at the base of the lithospheres. But the mantle upwelling that happened in these areas causes the temperatures to rise within the crust. Continental crust being low melting point compared to the basalts, we have the upper continental crust taken mostly as granitic, where the lower one is slightly at a higher melting point. I forgot the exact melting relations right now, but we take it, the density is around 2,800 kg per meter cube, where the upper one is 2,700 kg per meter cube. So that what it causes, this mantle is increasing the temperature of the crust that it is coming in contact with, and causes its melting. Now, as time progresses, this is the time, what we can see is that this melting and the higher temperature causes this lithosphere or the continental crust to actually peel off. This is nothing but caused by the mechanical differences present inherently in between these two layers. Now, temperature just accentuates the differences and cause the lithospheric mantle plus parts of the lower crust to delaminate from the remaining upper crust. This is just like peeling off a layer of a cake, which has different properties. So as time progresses, then this convecting mantle is actually stabilizing this delamination process, and slowly parts of this, again, the continental lithospheric mantle and the lower crust is just getting delaminated, while the upper crust is forming the orogenic crust. However, contrary to a very thick orogenic crust that we see today, like the Himalayan or alpine type, in this case, this is a very thin orogenic crust. So this process, which we call peel back orogenic style, because it is substantially different from what we see in the modern Earth. The main reason is this: the higher temperature causes this changes dynamically within the system. So we termed this as a peel back orogenesis, and then we published in series of papers how these things can match to the natural observations. Now, coming to it, the natural observations, we need to find some proxy that can be predicted from the model, and then you can take to the field and calibrate it against the natural rock record. As I said before, I was more interested in studying the metamorphic rocks. So what I thought to do is to track certain part of the crust and track their PTT evolution. PTT means pressure temperature evolution with time. And that can be done because the model inherently has certain model setup has certain advantages to do so. I just shown this picture here where these are the model grids, fixed Eulerian grids. However, there are particles, these open boxes, which actually flow between these grids depending on the velocity field in the model. So as it happens, these markers, which Paris called markers, it carries the physical information of the rock type. That means the pressure, the temperature, and its other physical properties as this marker moves with time. So if you track one marker, you can see its evolution of a particular physical parameter through time. In this case, I intended to track the pressure and temperature. So what we did, we actually did for a huge amount of markers across the crust. Of course, I'm just showing a few just to illustrate what I'm going to show. So this is just put some markers at the base of the upper crust, in the middle of the crust. And these are the inherent pressure temperature conditions at a stable condition before the orogenesis kind of disrupted this area. Now, if I see now what happens as time progresses in the origin duration and the peeling and the delamination part hits this area, you can see how the crust is actually deforming. The blue markers area as shown is very down compared to its initial position, and that we can see in this diagram. So this diagram is pressure and temperature. Pressure is in GPa. So as you can see from here, this point, while it came to here, it actually increased in pressure, the blue ones. Similarly, the red ones. Now you can of course see the mobility of the displacement of the blue and red markers are not the same, and that's translated in their heating and the cooling paths, or the metamorphic evolution. But what it tells you is that the blue markers, if we take it for example, it was very down, increase in pressure and temperature, and then slowly again get placed at the bottom of this thickened area, relatively thickened area, which you can see here. And then afterward from here, which means here, it again exhumed back, more closer to the surface, which is shown by this decompressive path. So over the time of between 90 to 60 million years, almost 40 million years, the rocks, at least these blue markers, evolved or shown this PG path. Similarly, the red ones show a particular type and the black ones. What is interesting from this part is that if you take this diagram, we can see the dichotomy in the PT paths. Of course, there is much more pronounced, but as I said, I'm showing this with few markers. So one is this red one, which is showing a little bit of high temperature at lower pressures as compared to the blue ones, which shows high temperature, but also relatively high pressures. Now, these two rock types, or these two metamorphic types, are very apt to show the pair metamorphism on the 2.8. So what we did, this is again the temperature, the pressure, and on this, these are the different geothermal gradients based on the work of Mike Brown. And then these are the markers that we found from our models, while the green and the red field are the density field based on the natural data set. So when we overlapped, we found a reasonably good fit between the modeled marker data points and the natural data points. So for example, for one blue line, we found out the maximum temperature and the pressure condition at that temperature, and we use that to plot one point. So as you can see, there are more than 3,000 data points. 3,000, that means more than 3,500 markers, the data that we have put in this figure. So we can clearly see this dichotomy between a metamorphism that is happening mostly along this gradient and another one that is happening around 775 per degree per GPa gradient. So we said this aptly reconciles with the metamorphic data of the 2.8, or at least up to the till 2 billion years ago from today. And similarly, we also did for the magmatic rocks, which I'm not showing here, but this is shown in this paper, also the magmatic rock types. So if I just now correlate this with the cartoon diagram, where this blue one forms and where this red one forms, is this once this area, if you just take, here you can see that isotherms are depressed downwards, very much like the subduction zone or a collisional zone. So you actually form this thickening area with the colder geotherms, relatively colder geotherms, which is this area. So your isotherm is depressed. That means here you will form high pressure, relatively low temperature. So the metamorphism will happen along relatively colder thermal gradients. Whereas this area, like this area here, that means the area that is after the delamination happen, the crust becomes thin and it resides atop the hot mantle. So here the metamorphic overprinting will happen at a very high temperature but at low pressures. So that's the region where these red markers are getting overprinted by a very high temperature metamorphism, whereas the blue ones are mostly forming in this area and then somehow escaping this overprinting and coming back to the surface. So that's why we are getting this paired metamorphic signature from models, which at least quantitatively fits with the natural data set as well. Similarly, here I have also shown the magmatic part, which I won't go into detail, but I'm happy to answer anyone's questions. So this is about the PT path, but there's another thing which we can compare between the rock types and the model is the pressure time and temperature time. That means the burial or exhumation histories or the cooling or the heating histories. So I, again, tried to correlate the cooling histories present in the rock record compared to the cooling histories from the same markers. As you can see, we can track the PT across time, so it's easy to find the time temperature histories as well. So from the markers, we found out that for the blue ones, we can have a cooling rate starting between 10 to 31 degrees centigrade per million year. Sorry, I forgot to write the unit. And certain parts may have had cooling rates even less than 10. Whereas for the red ones, which are showing high temperature metamorphism and shallow pressures, they are having a wide variation in the cooling rates, some going down below 10 degrees centigrade, 10 degrees centigrade per million year, while the others are in the range of 20 to 30, similar to this one. So overall, if you see for this kind of high grade rocks, not the UHT, but for the ultra pressure, the high pressure granulite, the intermediate TYP rocks, we are showing some order of magnitude slower cooling than what we see on the modern Earth, or at least in the Variston compared to that. So I have compiled a data set which shows the changes in the cooling rate across time, which is present in this paper. And if you compare that, we can see that this gradients in the Archean were around the similar orders of magnitude, the cooling rates, as compared to the modern day, which is at least one order of magnitude higher than the Archean, around 100 to 500 degrees centigrade per million year. So this data also fits well with the metamorphic cooling rate that are at least known so far from the Archean terrains. The data sets are not, of course, robust. We do not have many data points as we go back in time, but whatever we have, it is consistent. So, but this is all part of the modeling. What I also did is that I tracked some rocks and then tried to figure out whether this PTT paths can we extract from the rock and directly correlate or compare with the models or not. So in that, I actually worked in my PhD part of Indian rocks, which is present in the southern granulite terrain. I'm not sure what many of you may know, but this has a very lot of attention because of its involvement in the supercontinental reconstruction. But this area, I'm not going into the details of the map, but this area, particularly in this part, has a history of metamorphism that goes back to 2.49 to 2.45 GA. And this rock somehow escaped, or at least do not show a visible overprinting of the later events, at least in the zircon or monazite record. So we typically choose those rocks. I particularly focused on one of the mafic granulites present in this area, and then try to find the pressure, temperature, and time histories from them. So the pressure temperature histories of using the classic metamorphic approach for conventional physical clear modeling, where we found that the rock itself is basically dry rock, that means just has garnet, plagioclase, and clinopyroxene at the peak assemblage, and then we have certain reaction textures denoting the retrograde or exhumation histories. So we found the peak temperature using this assemblage between garnet, pyroxene, and plagioclase, and using conventional geothermometers and geobarometers, and also physically where it falls at around this area. The yellow bar shows the estimates came from the conventional geothermobarometers, while the path shows the path that came from the isoplathermometry. So you can see a pretty good overlap. So for the peak condition, which is around 800 degrees centigrade up to 13 kilobars. So it falls within the realm of high pressure granulite metamorphism, the peak conditions. Then it decompressed and came into this area around 700 degrees centigrade, where we have this garnet breaking down into clinopyroxene and plagioclase in presence of relic quartz. And then we have this garnet breaking down another form, gram fuel and plagioclase, which must have happened in presence of fluid. So this phase diagram is actually a combination of two. So we performed one with presence of water to capture this part, while these two happen mostly in dry conditions, so have 700 degrees centigrade. So this part is the dry. So these are two different phase equilibrium calculations that we mixed. But this is basically the PT path that we predicted for this particular rock type, and it's consistent with the other PT paths that is found in that area for this episode of metamorphism. But now the idea is to find the time history or the time temperature history of this rock. And I did that using diffusion modeling. So this is like the garnet and chronometry stable at the peak conditions. So this grains, if I take the composition profile along this yellow line, it is shown here. The 0 is the interface, that means this area. And then you have the distance, where this is the mole fraction. Oh, I'm sorry, I just forgot. You have the, sorry, I forgot this part here. But this is basically the FEMG MNCA, and this is FENMG. What you can see is that mostly the garnet profiles are pretty flat. They have very little curvature around the zoning interface, but mostly it's flat, while the profile is mostly shown by kind of peroxine over the 15 micron distance or so. So we thought, okay, if we can find out that the time it took the chronometry to develop these profiles in presence of garnet, then we understand that this is a retrograde zoning. So we can find the duration of cooling from the peak conditions, since garnet and chronometry, these particular grains equilibrated at those conditions. So here you can better see. So the green one is the magnesium for the chronometry. The red one is the iron, where this is iron, this is magnesium, and this is manganese and calcium for the garnet. So for doing this diffusion modeling, what we need is a peak temperature that is from where the cooling started to cause this zoning. That we inferred that must have been 800 degrees centigrade, which is the peak estimate that we made from the thermobarometry. And then we required the diffusion coefficients of these elements in these phases, which we took from the experimental data. And then we needed a thermometric law, along which basically the log LNKD law, along which the garnet and chronometry will exchange iron and magnesium between them. So if you take all those things, and then what is left is that the initial compositional profile, that means what was the profile at this temperature from where cooling started. Now this is, we need to estimate based on the observation. So the safest observation that we can make is that, assuming that the composition at the geometric core of the grains is what was present at peak temperature. It may have been different, but we have no other way to find this. So that's why we take these horizontal profiles, similar to the in values to the composition present here, here, and at these parts. And we thought that, okay, if this is the initial profile, then we will see how much time it will take from straight to this part. And the only thing now that will control is the time temperature history, the cooling rates. And then we took arbitrary cooling rates a lot, various types of cooling rates, exponential, linear, nonlinear, stepwise. And we found a classic match. And this match is calibrated to statistics, the least square difference. And we found the best fit we get between the modeled data and the measured compositional data for this path. So if we take the 800 degree centigrade and cool it to 660 slowly, slowly means at this rate, and then suddenly change the cooling rate or increase it to a certain amount beyond this, then we can fit the data pretty well. Although the data fitting is mostly better in this part, as you can see, while this part, the data is not that great. It's still better than the other profiles that we have had, but it's not as smooth as this one. But then this also encounters a lot of problems in measuring the data, because this data is measured at the space of 1.5 micron. So we often get some effects on that. So based on this, we thought, okay, then we may have a nonlinear cooling in stepwise fashion for this particular rock. So we then did this calculation for a multiple garnet chronometry pairs from different thin sections. So on average, we found this two-stage cooling is consistent with at least all the samples that we have studied for this particular rock type. And the cooling rates are also consistent, that mostly we have a relatively slower cooling at higher temperatures, although it varies between 5 to 30, depending on which thermometer you choose, which diffusion coefficients you choose, because those are experimental and we have to tally this between the different studies. But so this varies between this, and below 650 degrees to 500 till the closure temperature, we have seen that the cooling is 70 degrees to 80 degrees with an average of 7. Most data are falling around 70 degrees centigrade. Now, when we started to think why this change in cooling rate happened, so we can see if we compare this cooling rates, the PT path, what it is showing is from the peak to the 650 roughly around, this slowing relatively slowly and then changed its pace. So that may have to do with the fact that at around this temperature, that's when the hydration started. And with the water influxing in, you slightly increase the cooling rate. Of course, the hydration is very limited, as we see in the rock type based on the textures. So therefore, it's not significantly altering the cooling rate, but it has certainly increased it. But based on now the upper part, the cooling at the higher temperatures, what we can fit is compared to the model is that for the high pressure granulates, the intermediate TYP rocks, which fits the criteria for our studied metamorphic rock as well, because as I said, this 800 degrees centigrade at 13 kilowatts, it falls in the high pressure granulate criteria. So for that, the predicted cooling rates are also in this range, 10 to 30 degree between 800 to 650. So we often thought, okay, then it has a good resemblance between the model data and the natural data. Of course, we cannot get these minute kinks in the natural data, but that's beyond the resolution. But of the overall, the average cooling rates are fitting well with what we predicted. So based on that, we thought, okay, maybe this particular rock type of this from this Indian terrain may be the signatures of this kind of orogenesis. But later on, many studies have shown that this orogenic style may have improved for other parts as well. But this is not to say that this is the only orogenic style that was prevalent throughout the globe at that time. Because as I said, mantle temperature, even at the present day, has a difference of 100 or 250 degrees centigrade. So for example, in southern parts, it is very hotter compared to the other parts. So this difference may have existed at any point of time. So therefore, the impact of those mantle temperatures on the lithosphere also may have varied at the same time, but between different places. And that may have also translated into certain variations in the tectonic regime. But overall, if we consider that the Earth was hotter back in time, then this process may have been more prevalent than the modern orogenic style at those time periods. So based on this argument, we kind of created this timeline on the orogenic evolution. So this is the basically metamorphic PT data and the modern results. But we may have had some sort of peelback-driven orogenesis that was dominating at Archean to some time between Proterozoic. This solid line shows the dominance. While it may have happened even throughout the as we progress towards present day, because even today we have in Apennines, all those places where hot lithospheres are involved, we do see this kind of delamination process in orogenic conditions. So, but of course, at a very restricted places. While we have this kind of situation mostly dominating the Phanerozoic part, but however, you may have had this kind of conditions in the Precambrian or at places where the mantle may have been colder, like the paper by Owen Wheeler and St. Onge, where they found Trans-Hudson may have behaved as a very Himalayan style at 1.8 GA around this time. And that may have been true. So this is how you may have different styles through time, but may have coexisted or overlapped in certain time periods as well. So with that, yeah, that's basically it. Thank you.
Okay, thank you very much, PD. Now it's time for questions from our participants. So feel free to open your mic or leave your question in the chat and I'll read it by your behalf. And I'm going to read a question that was asked in the earlier part of the attack, leaving a chat by Li Zhenxing from University of Science Technology China. Is asking about is the Archean lithosphere thicker or thinner than the modern lithosphere?
Sorry, the line got disconnected for a while. Did you ask something?
Yeah, there's a question in the chat in the earlier at the beginning of attack.
Right.
And,
sorry.
Yeah, is asking about thickness of the lithosphere. So is the
Yeah.
thickness lithosphere in Archean thicker or thinner than the modern lithosphere?
So of course, I think if you take the lithospheric melting, that means where the mantle melting starts, it should have been at a deeper level in the Archean because the geotherm, the idea that intersects the melting point of the mantle rocks at a deeper level. So therefore, you certainly have a greater melting depth, which relates to a greater amount of melting, and therefore you may expect a rather thicker lithosphere in the Archean. But what was the exact extent of that thickness as compared to present day, in my mind, is debatable. For example, we may have had cratons formed up to 200 kilometers, but that craton may not have formed in one go. And also there is a difference in the opinion how they have formed or how they have become that thick. But if I leave that aside and just think in terms of mantle melting, then yes, mantle did melt at a greater depths in the Archean than today, which means greater volume of magma generation, which means greater thickness. So by the simple analogy, it should be thicker.
Okay, so next question from Xu Jie in Frankfurt University. Xu Jie, please go ahead.
Thank you for nice talk. And I'm wondering how the rocks exhumation after the subduction if the mantle is hotter than now.
Yeah, let me just show you this part. This part. So what happens, as you can see in these areas, can you see, right?
Yeah.
Okay, this area, the things that slightly melt. So you can often, as I track the high temperature rocks, they are coming up through the sort of, I can't say plume, but sort of like a ductile deformation, and is coming or lodging at the base of this field of orogenic crust. And from there, it is mostly thrusted upwards because this area is relatively cold and can have fault zones. So that picture I haven't shown here, but there's a beautiful work by Perchuk in 2018, where they've actually showed the alignment of the fault and the planes and how the ductile flow may have been occurring at a much higher resolution in the top part, like in this part. So there you can see how the rocks actually move. So once you bring these rocks to these depths, melt them, they move up into buoyancy, cool in the lower crust. As you can see, this is the molten part. And from there, they can go through the channel or the fault planes or the shear zones, rather, not, I shouldn't say fault planes, but on the shear zones, and then move at the middle crust emplacements, middle crust depths. So that's for the high grade rocks. At the shallower grade, that's a tricky part, but then you can have a thrust type events like in these areas. Let me see if I have this. Sorry, I do not have this picture, but in these areas where you can see sedimentary wedges forming at relatively low temperature. So there you have actually like thrusted sheets. So just like modern day wedges, sedimentary wedges. Sorry, that answers your question.
Thank you. And what's the difference of the density of the crust and the mantle?
Oh, so the initial, as I said, this white part is 2700. And then the lower crust, actually, I took for different composition, a little bit andesitic. Then this is actually very mafic, I think 2900 something. But then these values change depending on the pressure temperature conditions, depending for the equation of state. For the mantle also, we have the composition given in pyrolytic, and then we calculate the density based on the Gibbs free energy minimization in the code. But you can assume at the surface level, that means at zero at this pressure, surface pressure, it is 2700, while this should be around 3.32 to 3.33 gram per cc. Well, this is 2.7, and this may be 2.8, 2.9, depending on the model which I take. Because all these values are actually are tested over a range to see its effect.
Yeah.
So, but there's all these values are based on also the natural data that we have.
Yeah. Thank you.
Thank you.
Okay, next question, please. Feel free to open your mic or leave a question in the chat, and I could read it on behalf.
Okay, I see someone.
So there's also a question from Li Zhenxing there about the TP ratio of the slab.
Yeah, so T by P, okay, let me just take a time to describe this.
There's a hot subduction more.
Yeah, so this is, yeah, so this area you can see is really, it's hotter compared to the present day subduction zones. But I wouldn't call this a subduction, although it mimics the architecture or the thermal architecture of a subduction zone, because this is actually a continental lithosphere undergoing delamination. So it actually looks very similar to subduction zone, but still it is not subduction. The sensu stricto subduction is this part, which happens in the initial part, and then it ends through the slab detachment, and then this process kicks in where you're delaminating this thing. Now the T by P is, sorry, it's better to show in here. T by P is something that you get from your rock. For example, if your rock is metamorphosing, sorry, I increased it. But your rock is at this condition, right? This blue one. So it is following some geotherm, maybe this one. Now T by P, then the gradient of metamorphism should be the line that is intersecting all these isotherms. So that is your geotherm. And assuming that this rock is actually equilibrating at that pressure temperature, the peak conditions, then the temperature, the peak temperature, and the pressure at which it attains the peak temperature becomes a proxy of this line. So that is what the T by P, or the thermal gradient, or apparent thermal gradient means. So was I clear or was I not? I hope I answered the question, or let me know.
Okay. The next question from Chantal Liu from Zhejiang University. So he's asking about when did the modern tectonic regime start, most likely, so in your opinion?
Yeah, so as I said, this over the years, I think whatever little work I've done, I've started to realize that it's not a one-time instant that you can say, okay, at this hour, modern plate tectonics switched into. But if I have to call a time period, it should be sometime in the Neoproterozoic. To the best of the rock record that we have, you may have started the situation to create modern plate tectonics at some places even before Neoproterozoic, as certainly we are getting rock types of more and more colder thermal gradients like the eclogites. But on a more prevalent basis across the globe, we may have had that part going on in the Neoproterozoic, around 1 GA or 1.2 GA, around that. So that's where I put this green line. So certainly the solid part shows certainly we have had this, because based on the rock record, but it can be extrapolated up to this. So this time between 1 to 2, we may have been in a hodgepodge situation.
Okay, so a following up question from Chantal Liu is that, is that reliable for the geochemical record? For example, depleted niobium at the tantrum of the early existing plate tectonics. So do you think those are the geochemical?
So not to piss off geochemists, but the problem is niobium tantalum, they track certain things like the calcium magmatism, the role of water, and all those things. Now, even in this kind of situation, you can have water influx and all those things coming in. So you may get the same signature based on the geochemistry, absolutely. And that has been shown by recent works of Tim Johnson and Hugh Smith. If you look at their Nature paper in 2022 or 1, I forgot, but where they show that the source of water is what matters as well. It's not just the presence of water. And now many people are working on that as well, even using titanium isotopes and all those things. So we may have had the involvement of water in the making of Archean continental crust. And we need water to make felsic continental crust, that's for sure. But by which mechanism that water is actually getting into the deeper parts of the crust, or in this case, going from surface to down, subduction is one way, not the only way. So nowadays we are realizing that even to dripping mechanisms and all those things, you can take water to a deeper depths, and that can cause calculoclonamagmatism. So your niobium tantalum and all those things that are based on that, the arc signature can be imparted to those things as well. So that's the part I just showed. If you're just looking at one proxy, be it anything, and just taking it and extrapolating it to say this is global plate tectonics or not, then we could be misleading. And same goes for metamorphic, by the way, as well. So this one, as in the APSL paper, I read with magmatism and metamorphism. So combining all the proxies, I think we should be safe to say that we may have started some form of plate tectonic styles by the end of late Archean, but its style evolved through time, just like a baby growing into a human being. It goes through different phases. It doesn't look like it looks like a 30 years old right from the day he or she is born. So that's what may have happened with plate tectonics.
Okay, so next question, Umigash from IIT Kharagpur.
Yeah, hello. Yeah, it was a very nice talk. Thank you. So
Thank you.
I just wanted to ask that in the numerical model, like the geodynamical modeling that you showed. So how do you like estimate the thickness of the plates? Like how is it calculated?
Thickness of the plates come naturally as a function of the mantle potential temperature. So what will be the thickness of the lid, conductive lid? If you go for the convection models, you will see a boundary layer forming. So that boundary layer is automatically stabilizes based on your Rayleigh number value, and the Rayleigh number is controlled by different things. And a good way also to check is that you can start with any arbitrary thickness, and then you will realize if your thickness is too small, that means you have a very thin lithosphere, then you have a huge partially molten mantle lithosphere, which means at that part, mantle is not stable in its original form and it is melting. That means it is experiencing decompression. So you need to increase the thickness. And if your lithosphere is extremely thick compared to what it should be, then you will see that your mantle convection is actually eroding out the excess part.
Okay.
That's called thermal erosion of the lithosphere also. But this is all under the ideal conditions. You may also ask that in present day, we have different thicknesses, somewhere very thin, somewhere very thick. But those have a different mechanical properties, and that's why it changes the Rayleigh number effectively. So yeah, but effectively in the models, it comes out as a function of the mantle thermal and physical properties.
Okay, thank you. And another question I wanted to ask is the like PT thermodynamical PT graph that you showed, the thermocalc or perplex model. So there you
This
showed that
one,
after after the fluid comes in, the direction of the curve changes. So can we quantify the amount of fluid, or like till how much amount of fluid can it be plotted in this PT graph? Because after a point of time, it will be an open system. Like if there is like large amount of fluid.
Yes, of course you can calculate. So you can create a TXH2 diagram, and you can find out what is the amount of, or MH2, depending on in what form you're casting the equations. And you can find what is the maximum or minimum amount of water that you need to stabilize the assemblage that you observe.
Okay.
So even it is an open system, it is an infinite, in fact, is an open system. The moment you enter water, it is an open system. But whether you are making fluid saturated or you're taking a certain value, that comes from the observations from the rock. Because once you change the water value, or rather the activity of water, then the assemblages also change. So what you are seeing must be present at certain window. That window you can find out through this TXH2 diagrams.
Okay.
So I think for this one, I forgot what is the exact value, but it's around 1% or something. It's very nominal water content.
Thank you.
Thank you.
Okay, there's one question from Zheng Xing in the chat, and he's talking about refer to a publication talking about the high the hot subduction, intermediate temperature subduction are not always in the same area.
Yeah. So sorry, I haven't seen the paper. I will definitely look. But yeah, the idea is that you don't have to have from the same area. It may be from the same area, or it may be from a close by area that can be juxtaposed against each other. That also happens. So, but that does not take into account the fact that you can, it is not the exclusive part. So even if in these models, you can see that, so there's quite a lateral So this is around 600 kilometers on the x-axis. So you can find these rocks wide apart in the field, or maybe later juxtaposed together when this phase or this lithosphere will be subjected to further orogenesis process, because the disposition that we see today may have been affected by multiple events. So I completely agree with you that you do not have to form these kind of rocks at the same place, but often they are related to same tectonic environment, if not in the same place. And the cases where they are completely tectonically juxtaposed and have no relation as so whatsoever in terms of the genesis, that's a very exclusive in cases. So that I cannot consider in this case. If that answers your question.
Okay. I have a question. I think it's relatively simple that in your orogeny models, from your perspective, does this orogeny promote the emergence of the crust above the sea level or not?
No, it does. It does. So even what happens, your orogeny crust is thin because of the delamination process. What it also does, it takes away the denser lithospheric mantle part and the lower crust, which is actually, if you think of the isostasy, it will pull things down. So once that is gone, you have upliftment of the orogeny crust, but more likely in the form of a plateau rather than a mountain belt, but over a wide area. So you will certainly have a upliftment in the area for sure. But the extent of it, sorry.
Yeah, I see another side of the story is that as this orogeny goes, to me that looks like there is an expansion of an ocean basin that likely will drive down the elevation of water in the ocean.
So the initial part.
I think including this model. I think including the
No, you have a huge mantle melting, that's for sure, but it will not lead to a oceanic. So once this part starts in the orogenesis, so here you may have a lot of mantle melting, mafic magmatism, just preceding the start of the convergence between the two continental plates. So once that starts, you again have a mantle melting, undoubtedly. Here we have suppressed that in the model just to see the effect on the crust, but you will have a mantle melting in this area, and that will produce your mafic lower crust, but not an oceanic crust per se. So eventually, when this lower crust will accrete to the base of this orogenic crust and a lithosphere will grow, then again it will subside. But that happens over a million time period of 200 of years, more than that time period. But till then, there will be upliftment when this is all going on, because at that time, still you do not have the lithospheric mantle formed.
Okay. The problem I had some misunderstanding that for this model you are showing in this slide, there is no oceanic crust.
No, there was oceanic crust beforehand. So yeah, but once that is gone away, the subsequent development is between the continental plates.
Oh, okay.
Sorry about that. Yeah.
Okay, it's like a. Okay. It's a probably could give example of the Tethys Ocean. That could be gone. Okay. I think that's the end of our webinar today. So let's open our video to everyone to end this webinar and smile and show your appreciation for our speaker, PD today. So everybody, could you open your video and smile, and then we are going to end the meeting. Maybe with a good group photo, I suppose. Okay, everyone, could you open your video? It's just very fast. Just 30 seconds. I think it's more than that.
No, thank you for inviting.
Okay, I think that's so much for today. And next Wednesday, we have our next speaker, Kate from Ireland speaking. Okay, have a good day. Have a good day, everyone. Have a good day, PD. Thank you.
Good day. Thanks for having me.